My name is Niklas Risse, and I will be presenting our paper Uncovering the Limits of Machine Learning for Automatic Vulnerability Detection. This is joint work with Marcel Böhme, and we are from the Max Planck Institute for Security and Privacy from Bochum, Germany. And we are also funded by CASA, which is also located in Bochum in Germany. So, are machine learning techniques such as large language models actually good at the task of vulnerability detection? Well, basically they have achieved some promising results when we wrote this paper. So basically there is this code XLU benchmark, which is based on the Divine dataset, and they basically test different machine learning techniques on the task of vulnerability detection in terms of classifying C functions for whether they contain a security vulnerability or not. And basically they found several large language models, such as the UNIX coder model, to achieve some promising results. So, for example, this UNIX coder model achieved an accuracy of 70% or close to 70% on this benchmark, which means, because this dataset is actually class balanced, this means that in 7 out of 10 times, this model was able to deliver a correct decision. So let's look a little bit deeper into this benchmark. What is actually tested in this benchmark? So basically, this Divine dataset, which is used in the benchmark, consists of C functions, and these C functions may or may not contain security vulnerabilities. So for example, in this case, this C function contains a divide by 0 vulnerability. If the function argument num splits is 0, this function basically crashes and leads to exploitable vulnerability. And basically, in order to compute these accuracy scores, the researchers fed a lot of these functions into these machine learning models. And if they were able to deliver the correct prediction, so this function is vulnerable, then they were marked as correct. And then this way, you achieve this 70% accuracy. So do these promising scores actually mean that these models are good at vulnerability detection? Or are there maybe some alternative explanation for these high scores? So in order to investigate this, we utilized a tool called semantic preserving transformations. And semantic preserving transformations basically change some superficial properties of the code. So for example, here in this case, I renamed all of the function arguments to different names and applied these changes consistently across the function. So this way, basically, I did not change anything about the semantics or the functionality of the function, and also did not change whether it contains a security vulnerability, but basically I just made it look a little bit different. And actually applying these transformations to this data may actually lead to the machine learning techniques to change their prediction from a correct prediction to an incorrect prediction. And we actually implemented a set of these transformations. So we implemented 11 of these transformations. So for example, we had transformations which added or removed comments, which removed or added unexecuted code, which we had the transformation which split a function into 2 functions. We had transformations which rename variables or function names or other identifiers. And we also had the transformation which reordered some unrelated statements. So for example, simply the function arguments. Yes, and the first research question we asked was, how is the performance of these large language models affected if we transform the functions in the testing data using our semantic preserving transformations, so without affecting the semantics of the code? In order to do this, we first had to establish a baseline. So we basically used the standard evaluation setup, which is also used in the code XLU benchmark, where we fine-tuned these LLMs using a training dataset and a testing dataset. And we basically just used the Divine dataset, which is also used in the benchmark. And this led to these accuracy scores, basically the same ones which they got in the benchmark. So we basically took the 6 best performing models from this benchmark, and then this led to these scores. So each star basically marks one of the accuracies. And then, in order to answer our research question, we basically made copies of the testing dataset and transformed each of the copies by applying one of our transformations to all of the functions in the testing dataset copy. And the results actually show that this leads to a drastic decrease of the accuracy of these large language models. So interestingly, we only changed some superficial properties of this code. So if they were actually good at vulnerability detection, we would expect them to have the same accuracy, because we didn't change anything about the fact that they may or may not contain security vulnerabilities. But as it shows basically the performance was drastically decreased. So to answer our research question, the performance is drastically reduced if we transform the functions. So then we went a step further, because this was also suggested by previous work. There's basically a technique to basically solve this problem in a way. And this is called data augmentation, and basically you can just apply the same transformations which you apply to the testing data also to the training data. And we basically did this, and it shows that basically the accuracy is in most cases close to or almost fully recovered. If you also basically show the LLM that these functions can have different superficial properties, can look different, but still be the same functions and still contain the same security vulnerabilities. So basically, yes, we can restore the performance by transforming the training data as well. So is the problem solved? And we basically even went a step further and asked, does this gain robustness, which we gain by basically augmenting the training data, actually generalize to new transformations? So let's say we have a set of transformations, and we can now basically apply a subset of these transformations to the training data and a different subset to the testing data. And this is basically our third step. So basically we just applied different transformations to the training data as we did to the testing data, and did this for all possible pairs of transformations that we have in our set. And interestingly, we get very similar results to the first round, where we only applied these transformations to the testing data. And this means that even though we basically taught the LLM that a function might look very different and might have some different superficial properties, this basically only helps for the superficial properties that we show it, and not for new properties which we introduce. So to answer our question, does the restoration generalize to new transformations? No, it does not. And basically one of our key findings is that these large language models basically overfit in a way to these superficial features of the code which we introduced using these semantic preserving transformations. And we basically can only recover the performance if we transform the training data in exactly the same way as the testing data. So given these findings, what can we now say about large language models actually being able to detect security vulnerabilities? So to test this, we basically had a second experiment where we introduced a new data set called vuln-patch pairs. And in vuln-patch pairs, basically we have collected a data set which consists of vulnerable functions and their patched counterparts. So we basically just extracted vulnerable functions from open source repositories and also collected the versions of these functions after they were patched by the developers of the repositories. This gives us like a pairwise data set. And what is very interesting about this data set is that you have these pairs, and these pairs might be only very slightly different in terms of their look, but they are very different in terms of their meaning, because one is vulnerable and one is secure, basically. And we of course, asked the obvious question, can large language models actually distinguish between vulnerable functions and their patched counterparts? So basically, we again took the 6 large language models which achieved the highest scores on the code-exclu benchmark. Here you can see this, again, the scores which we reproduced on the benchmark, and then we took these 6 models and actually evaluated them on our new dataset vuln-patch pairs. And as you can see, the scores are actually quite bad. So this dataset is actually fully class balanced. So even a random guessing algorithm would achieve an accuracy of around 50%. And as you can see, all of these large language models achieved scores like close to 50%, some even lower. So basically, we can answer our research question. So large language models cannot actually distinguish between vulnerabilities and their patches. So as a conclusion, basically, as we have shown in our first experiment, large language models are actually good at pattern matching. So if you give them training data, and in your testing data, or basically in the real world, if the data on which it is used is very similar to the training data, then large language models perform really well. But in the case of vulnerability detection, this is actually not what we want, because in vulnerability detection, a function that is vulnerable can look very similar to a function which is secure, but these functions might have a totally different meaning. And as we have shown, this leads to large language models actually not being really successful in this. So thank you, and I'm happy to answer any questions.